Welcome to the lecture of Communication System Engineering. Today we are going to discuss different types of sampling. We have already discussed sampling theory in detail in our last lecture and how it is happening and what are the different cases for the sampling like undersampling, critical sampling and oversampling. So in this we are going to discuss the types of the sampling. So the first type of the sampling is known as ideal sampling, and the ideal sampling is simply the multiplication of the input signal like the continuous signal with the pulse train, so whose frequency is f of s. We note that the principle of ideal frequency is just simply the multiplication, means you are multiplying the pulse train, and we know that the pulse train is like this. From minus infinity to infinity, so this is delta ts of t, and then you are multiplying this pulse train with your analog signal. So suppose if you have analog continuous signal is something like that t and your xt. So this is your continuous signal, and you wanna convert that continuous signal into the discrete signal using the ideal sampling. The circuit of the ideal sampling is given by this circuit xt, and so this is the switch who is on off depending on the sampling frequency, and we should know that what is the sampling frequency, which is equals to twice the modulating frequency. So this switch is on and off, on and off, on and off depending on the sampling frequency. So when the switch is on, we are getting xt at the output, like the trajectory of the xt at the output with the certain amplitude. When the switch is off, so when the switch is off, we are getting no output, like the output will be 0. So in that case you can represent the discrete signal in this format. So it means that you are multiplying gt is equals to xt multiplied by the pulse train. So you are quantizing the signal like this. So here you can consider that the width of the pulse width is 0. The pulse width is 0, which is practically impossible that the pulse width is 0. So that is why the noise interference is very high in this case, because the pulse width is 0. So that is why the energy of the signal will be very low. Like if you multiply xt with the pulse train, you can write the gt in time domain xt, and then multiply pulse train. Pulse train is delta t minus n of ts. So if you want to write this time domain signal in the frequency domain, you can write gw with this equation, and so this is the frequency domain signal. You need to note these 2 points, that the noise interference is very high. Why very high? I already told you that since the pulse width is nearly 0. So if the pulse width is nearly 0, so that means that the signal energy is very low. So if the signal energy is very low, then it is easy for the noise to interrupt the signal. Second thing, practically it is not used because the pulse width is 0, so that is why practically it has not much importance. Second type is the natural sampling. So the principle of natural sampling is chopping, so it is used chopping. Like here in this case you are using CT, so a continuous pulse with a fixed pulse width, and then you have xt at the input. So it means that you are multiplying xt with that pulse, and then you will end up with the gt. So what is the ct? ct is equals to tau a. So a is the amplitude. Like now in this case you can write ct in this format, like ct is equals to t So this is Ct. So the amplitude is A and the width of the pulse is tau. The tau is the pulse width, and A is the amplitude. So that is why you can write Ct is equals to tau A divided by Ts, and then sinc f of n tau e raised to the power j 2 pi f of s t. So if you like, if your switch is closed, in this case if your switch is closed, your xt will be the output after multiplying with this pulse. But if the switch is open, your output is 0. Like if the open, you can say open switch, so your gt is equals to 0, and then close switch, so gt will be some positive value, like depending on the ct. So the time domain signal, you can write tau a ts xt sinc of f of n tau exponential j2 pi f of st, and you can write the signal in this format. So these are the pulses, or like this is the chopping type, and this is the pulses which has a certain width. Which has certain width means that the pulses have a more energy as compared to the ideal frequency. So you can write in term of frequency domain as well. So frequency domain tau a ts, and then sine n of f as tau x f minus n of f of s. So this type of sampling has a less noise interference, and it is practically used. Why it is less noise interference? Because now it has a certain the signal energy is greater as compared to the ideal sampling. So that is why if the signal energy is greater, then the noise energy will be less, and practically it is used. This third type is the flat top sampling. Flat top sampling, and the principle of the flat top sampling is sample and hold. So you can also call it a PAM, pulse amplitude modulation. So you are using here the circuit diagram of that is xt and switch 1. So switch 1 is sampling. So this switch is used as a sampling. So means you are collecting sampler, and this switch is used as a discharging. And you are using pulse train delta tau ts at this position. So it means that when you press S1, so when you press F1, you are getting output, and then when you press S2, so your signal is discharging through this capacitor, and then you are not getting any output. But if you press S1, you get samples at the output, but if you press S2, you are getting nothing at the output. Your input is discharging through this capacitor. So in this case, pulse train is also delta t minus n of ts, but here you are first, when you press S1, so you are getting first output st. So st is equals to your xt multiplied with the pulse train. So means that you have a analog signal, you have a continuous signal. So this is time, and this is xt, and so we have delta, so like the pulse train minus ts minus 2 ts 0 ts 2 ts 3 ts, and then so on. So this is delta ts of t. So when you multiply xt with the pulse train, you are getting st, means that you are getting samples at the st. So these are the samples that you are getting. So ts, like your trajectory of the signal, and samples at the particular point, minus 2 ts, ts, 2 ts, and then so on. And then if you are using sample and hold, so gt will be equals to this st and then multiplied by the ht. So we have already discussed HT in our previous lecture. So if you want to see more detail, you need to go to in our previous lecture, and then there you can find what is HT, what is the response of the HT. So GT is will be equals to ST multiplied by the HT. So ST is equals to XT, and then HT is your pulse. So where the pulse is written as HT minus NT of S. So it means that you are getting the pulse similar like the natural sampling. So natural sampling, so you are getting some pulse width, means that you are getting some signal energy at the output. So this practical, so you can write the time domain signal in this format and your frequency domain signal in this format. Now, so practically you can use this signal by, and the second thing, because you are using the pulse train and the this method of generating samples is have very noise interference, means the noise interference is very high in this method, and practically you can use this method, and it is also it looks like a natural sampling, and it is also easy to generate this method. So these are the three simple methods that you have seen in the sampling theory circuit. So I hope that you understand these three types of different types of sampling. So if you have any question, or you want to ask any question about the sampling theory or about the sampling type, we can discuss in more detail. You can ask in the comment box, and there we can discuss in more detail all these any type of the sampling theory. Thank you for watching the video.